In this video, we'll discuss a few applications of integral. So one of the very important observation here is called net change axiom, net change theorem. So this is called net change theorem. So do a definite integral, you get a net change of some quantity. So this is called net change theorem. It has application in physics and biology and thing, right? So what's the net change theorem? So basically, the integral of a rate of change, if you are given the rate of change, right, is the net change, right? The actual change of the rate of change of some quantity, right? That is the actual change of net change of the quantity. So what's the meaning of that is integration from A to B f prime of x dx by the fundamental theorem of calculus. We know this is just the f of B minus f of A, right? This make connection between the rate of change and the net change. So that's a very nice result. But it's a very straightforward result from the fundamental theorem, right? This is the rate of change. This is a net change, right? Two specific examples. The first one, if you are given the rate of growth, right? So this is also the rate of growth of some population of a population is the dn over dt for sure, right? N here is the population and t the time, right? N here represents the population and t here the time, either by year or by day or by decades, right? So the integration from t1 to t2 dn over dt, right? dt. So this is nothing but nt2 minus nt1, which is a net change in population. So this is a net change in population during the interval from T1 to T2, right? So that's straightforward to see. Direct application of the net change theorem, right? So if you have a different in physics, one of the very fundamental rate of change is a position function, right? Suppose you have an object moving in a straight line, line, right? And we are giving a function s of t here is a position function of the object, position function. And by the duality, we know that the rate of change v of t equal to s prime of t. So that will be the velocity function, right? Velocity of such an object. Velocity, right? By the net change theorem, integration from t1 to t2, v of t dt equal to s t2 minus s t1. On the right side, you get net change of the position, which is also called the displacement. Displacement of the object during the time interval from t1 to t2. But sometimes you want to evaluate the distance, right? The distance is basically the integration from t1 to t2, the absolute value of v of t dt. So that's the distance traveled by the object during the interval from t1 to t2, right? Distance traveled by the object during t1, t2, right? So that's how do we calculate it. So let's see an example, right? Let's see example for this application in physics. We are given we are for sure we are assuming we have an object or particle moving in a straight line, right? And then we detected the velocity v of t is always 3t minus 5, right? So this on the interval 3, 0, 3, right? So we want to know the displacement of this particle on the interval 0, 3. And also we want to know the distance traveled by the particle, right? So let's try to calculate displacement first. Displacement. This is integration from 0 to 3, v of t dt. So this is integration from 0 to 3, 3t minus 5 dt. So this is 3 over 2t squared minus 5t. Then we plug in 0, plug in 3. So this is 3 times 3 squared over 2 minus 5 times 3. Right? So that's basically the displacement traveled by the particle from time on the during the time interval from 0 to 3, right? So let's try to calculate distance as an interesting integral, right? Distance by our discussion basically is integration from 0 to 3, the absolute value of v of t dt, right? So plugging our function, this is integration from 0 to 3, 3t minus 5 dt. We don't have any idea how to integrate the absolute value function. So we want to get rid of the absolute value sign, right? You can see that 3t minus 5 equal to 0 when t equal to 5 over 3, right? So when t here less than 5 over 3, 3t minus 5 less than 0, and t here greater than 5 over 3, 3t minus 5 is greater or greater than 0, right? So this is just some easy observation from our function. Based on this observation, right, 5 over 3 is between 0 and 3 because, right, this number is less than 2, greater than 1. So we can use the property of integral to split it into two smaller integrals. So this is integration from 0 to 5 over 3, 3t minus 5 dt, plus integration from 5 over 3 to 3, 3t minus 5, then dt, right? On the first part, inside is negative. Just put a negative, you can get rid of the absolute value, right? So that's equal to integration from 0 to 5 over 3, negative 3t minus 5 dt. Then plus integration from 5 over 3 to 3. On the right side of 5 over 3, the term inside absolute value is positive, so we can get rid of that directly, right? Because that's positive. So that's how do we get rid of absolute value? Divide your interval from lower bound to upper bound to smaller pieces. You can decide on each piece, on each subinterval, the term inside the absolute value is positive or negative, right? Okay, so let's try to finish it in the next page, right? So this is figure out the antiguity, which is negative 3 over 2t squared minus 5t. We have done that. For plug in 0, plug in 5 over 3. Then plus 3 over 2t squared minus 5t. Then plug in 3, plug in 5 over 3, and do a subtraction, right? So this is negative 3 over 2, 5 over 3 square minus 5 times 5 over 3. Then plus, plug in 3, you get 3 over 2, 3 square, you plug in 0. For the first term, plug in 0, you get 0, right? Minus 5 times 3. Then minus, plug in that number again. So this is what? This is 3 over 2 5 over 3 square minus 5 times 5 over 3, right? So this is basically the distance traveled by the particle during the time interval from 0 to 3. We have to handle an integral with an absolute value function inside. What we do is we just divide our interval into two pieces. On one piece, the term in the absolute value is positive. The other one, on the term inside the absolute value is negative or positive, right? You can get rid of that absolute value sign by dividing the integral into two smaller integrals.